Yesterday we looked at elastic forces, and there was an activity I wanted to do, but we didn't have time for, so we're going to do it today. First of all, before we do that, are there any comments, questions, concerns about any of the homework I gave you yesterday? Does anyone want to see any of these 4 questions done on spring constant? Sorry? No, that was the IIBs outside said something. If you did not have a chance to look at them, you will have time likely today to do that. But if you did look at them and you want me to go over any of them, I'm happy to do that. Now, Dana, did you do 4? You tried, that's all I ask. Okay, cool. Number 4, a spring is hung vertically and has a rest length of 6 centimeters. So I'm going to go down here and I'm going to draw out 4. Here's what's happening. We have it hanging, and we are told that the rest length from here to here is 6 centimeters. When a 1 kilogram mass is hung from the end, the spring stretches to a length of 11 centimeters. So let's draw that out. And we've got a 1 kilogram mass hanging here. And this total length is 11 centimeters. And we are asked, what is the spring constant of the spring? And what the length will be if we put a 0.7 kilogram mass on it. So if we draw can we even see that? That's really faint. If we draw the free body diagram on the second one that I drew, what forces are acting on that mass? Dana. The easy force that is always acting every time you are on Earth is what? Fg. Fg is straight down. And this one's easy because Fg equals mg. M is 1, g is 9.8. So that's a force downwards of 9.8 newtons. But the mass isn't falling to the ground, so there has to be another force acting up on the thing. What's the force acting up? N, it only exists if the thing is sitting on a surface. Is the block sitting on a surface? No, it's being hung by a... What's it being hanging by? A spring. So that must mean that there is an elastic force upwards on the thing, not a normal force acting upwards on the thing. And we want to find it. We don't know what Fe is, or actually we do know what Fe is. If that block's not moving, what's Fe? Sorry? No, it is not 0. Louder. Yes, the 9.8s. Yes. Why is it 9.8? Well, if the thing's not moving, Fg has to equal Fe. So that means Fg, which is 9.8, has to equal the spring force because this thing's at rest. So now we can start to plug these things in. 9.8 is going to equal Kx. Do we know what the extension of the spring is? Jack, would you do me a favor and shut the door? Because those IBs are loud. Dana, what is the extension of the spring? It was 6 centimeters. It is now 11 centimeters. How far has it been stretched? It was 6 and now it's 11. 5. So this here is the extension of 5 centimeters. So, but we don't want that in centimeters, we want that in meters. So if I divide 5 by 100, I'm going to get 0.05. And so now this is the extension that we can plug into here to figure out the K value for the spring. So we're going to get 9.8 is going to equal K times 0.05. To find K, I'm going to divide both sides by 0.05. And we're going to get a K value of something bigger. 9.8 divided by 0.05. 196 newtons per meter. That is the K value for this spring. And now, sorry, Dana, we good with what just happened? Okay. Hey, shh. Whisper. You're not whispering, you're just talking quieter. It's different. Feel free to whisper. This is whispering where your voice is gone. This is just talking quietly. I can still hear you. So it's for all y'all. Sorry if I'm short-tempered. My last Science 10 block pushed me over the edge. Okay, so now, Dana, this value for K is always going to be the value. It's a spring constant. It does not change. If this spring is being used, assuming we don't wreck the spring, this is the value for all time. So now the next question asks, what will the length of the spring be if we put a 0.7 kilogram mass on it? So now, presumably, it's going to be shorter because 1 kilogram is more than 0.7. So if we decrease the mass, we're going to decrease the extension, presumably. So let's draw what we're doing here now. It's going to be slightly shorter. It's going to be longer than the stretch. Sorry, longer than the rest, but shorter than the stretch. So that's going to be 0.7 kgs. If I draw the free body diagram here, I'm going to have Fg, and we're going to have Fe. Those are going to be equal. So in part B here, I've got Fe equals Fg. Fg is going to be mg, so that's going to be 0.7 times 9.8. And Fe is going to be kx, and we know what the value for k is. K is 196. That was the whole point of part A. So 196 times x equals 0.7 times 9.8. To solve this thing for x, we're going to divide by 196. And we're going to get that x is going to be equal to, it's going to be more than 0, less than 0.05. 0.7 times 9.8 divided by 196, it's 0.035. And that number is in meters. So have we actually answered the question? The question said, what length will the spring be if we put the mass on it? No. What do we have to do? What is it? What is this? Okay, so we'll multiply by 100 and we're going to get 3.5 centimeters. Have we answered the question? No. What is this? This is the extension. So the length that you added to the rest length. So how long is the whole spring now from the top down to where it rests? If we added 3.5 centimeters to it, how long did it start? It was it is 9.5. The length equals 9.5 centimeters. We found the extension, but the question asks for the total length. So if you add the extension to the rest length, you'll get the new length at 0.7 kilograms. And that makes sense. A 1 kilogram mass stretched it to 11. It was 6 to start. And so we're somewhere in the middle, adding a mass that's more than 0 and less than 1 kilogram. Does that, Dana, does that answer your questions? Okay, cool. Okay, comments, questions, concerns. Okay, so this is a simplified version. This question, if you're cool with this question, is a simplified version of what we're going to look at today. So flip back a page. By a page, I mean 2 pages. And this spring constant activity is what we're going to take a look at today. So the purpose of this activity is to find the spring constant of a spring or rubber band. I am going to give you and a partner, you are allowed to work in twos. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 24. There's an even number of you. Fantastic. You're working in pairs to find the spring constant of a rubber band. I will give you the rubber band in a second. Good morning. Hey, what's up? I do. Can I send him down later in the block, or does it have to be right now? I would appreciate that, but I will send him. Okay. Okay. Thank you. Bye. Kale, have you done that stupid student learning survey? Okay. Then when you and Kai, I'm assuming you're working with Kai, maybe it's you and Marcos, I don't know. When you have found the spring constant, when you finish this, you are to go down to Miss Fleming's office and do that silly survey. She's one of the vice principals. She's the, if you walk into the office, it's the 1, 2, 3, third office in, I think. It's either the second or the third. It's not the first, it's not the fourth. Yeah, you've dodged it for this long, but they're going to come get you. Apparently they care about those results. So here's what you're going to do. I will walk you through this and then I will free you. What you're going to do is you're not just going to do it once. You're going to do it a couple times. You're going to graph some data and you're going to find the result. That was a big sigh. Was that about graphing, Kai, or was that unrelated? Okay. So, step 1, you're going to do a bunch of masses. For each mass or collection of masses, you need to measure the mass in kilograms using the digital scales that are available to you as you hang them from the spring or rubber band. Do not assume that what is written on the mass is what it is. These masses get dropped, they lose mass. Somehow I've seen them gain mass. I don't know what's going on there. Whatever you grab from the bins, don't assume that what's printed on them is accurate. I don't know if you guys are aware, but these things actually clip together quite nicely. Lots of them they have obviously they have the hook on top. Some of them also have hooks on the bottom. These guys have holes or loop, like you can hook something here. So you can make this collection that kind of hangs as you go. I will ask, so these are the lightest ones. These are the lightest ones. If you take a mass from this little black tray, please return it to the little black tray. Mr. Morrison, Ms. Broad, and I are trying to keep them separate from all the rest of them. Be mindful of where you take your masses from. One of the quirks of rubber bands is that if you overstretch it, you can actually distort it, changing its K value. So start with small masses, don't make it too ridiculously big. Otherwise you will wreck your rubber band. And I don't care about the rubber bands, I don't necessarily want these back, but I do care if you impact your results negatively. So the masses are all up here. Today, rather than have you guys fight over the scales, I have tons of scales. These are all the scales. If it tells you to remove the lid before use, please remove the lid before use, and then put the lid back on the thing. Some of these are brand new. They have multiple lids. If they have this extra, just put the scale inside it like that, and then they've got another lid for you to take off, and it's brand new. No one has ever used this scale before. These things should measure to the nearest gram. So you will have to convert to kilograms for this. But you've got scales, you've got springs, rubber bands, and then where I want you to do this, I don't know if you guys have noticed yet, but all around the top of these whiteboards, so you might need to stand on chairs, on top of these whiteboards, all the way around the class, 1, 2, 3, 4, 5, 6, 7, 8, there's 9, 10, 11, 12, 13, 14, 15, 16 of these little hooks. I replaced screws with hooks. 1, so I can hang Christmas lights. 2, so I can do labs like this. What you're going to do is you're going to hang your rubber band on that thing. And the beauty of having it over top of the whiteboard is you guys can actually then mark on the whiteboards. Please do it on hooks that are over top of the whiteboard. You can actually mark where the rest length is for these things. And as you add masses, you're going to get extensions. You can then then you can make a mark on the whiteboard where it is hanging after you've added the mass. And then the difference between these two things is going to be your x value. So actually doing it on the whiteboard gives you a surface to do a bunch of work on. I will ask, yeah, sorry. Last semester I had students that were doing it on these numbers. As you can see, there's the results from one of these labs. Sure, go for it, but please do clean them off. That was last semester did. Once you're done using whatever surface. What you're going to do, what you're measuring on the scales is you're measuring the mass. But mass isn't something that we're going to graph. As we showed you in Dana's question number 4, adding the mass to this rubber band creates a force of gravity acting on the rubber band. So what you're going to do is you're going to take your mass, once you've measured it, that you're going to hang, you're going to change it into a force of gravity, and then you're going to measure the extension. You'll have already measured the equilibrium length here, and then you can go ahead and start to figure out what these extensions are. You're going to graph this thing. Now, when it's hanging static, the elastic force is going to equal the gravitational force, and the extension is going to be something that you measure. When you actually go ahead and graph this thing, I'll tell you now, I want you to graph it in reverse. I want your FE to be your dependent variable, and I want your extension to be the independent variable. Because that's going to be the only way we're going to get the results. Even though the elastic force is what you're changing, and the extension is what you're getting, when you graph the thing, graph it the other way. Graph it as though we were extending it to a particular length and measuring what the force would be at that particular extension. Otherwise, you don't get any cool results. Once you've got your 1, 2, 3, 4, 5, 6 results, you're going to graph them. FE is your dependent variable. Extension is your independent variable. You're going to draw the line of best fit. It should be straight. If it's not, then perhaps you distort it. If you distort your rubber band, you'll see a curve on your graph. It's going to be really easy to see. You're going to determine what the slope of the line represents. What should the y-intercept be? Can you see in your data where your spring or rubber band started to distort? Some of you may, some of you may not. Depends on how much mass you added. And how much should the elastic band stretch if you hung a 1 kilogram mass from it? So do not hang up. Don't go up to 100 kilograms. Sorry, to 100 kilograms, to a kilogram. I want you guys to deduce based on your other data what you get. I don't think, if you can keep it under 500 grams, like 500 grams would be your absolute max, I think you'll be okay. We'll see as we go. So that's what you guys are going to do now. Are there any comments, questions, concerns about what I'm asking you to do? Emma, was that a hand? 0 is going to be your equilibrium length. And then you'll pick a non-zero mass to start this thing. Keep it small. Like I said, you've got the little black trays there. You might have to share those, but you can grow from there. I'll be here to help, walk around. I have some stuff I have to grab from the lab first, so while you're working, the first couple minutes I'll be out, but that's what I want you guys to do. At the end of this all, you should have I do want to remind you of something. This should give you a straight line. So, if you recall, what is the equation for a line? What is the general equation for a line? It's not y equals 0. That's a specific line. Y equals mx plus b. This is the equation for the general equation for the line. If you're graphing FE as the dependent variable, where in this equation is it going to go? Is the dependent variable y or x? You don't think so? So you think it's y. You would be correct. You're going to get the elastic force is the dependent variable. It's going to go in the y spot, equals something times x. Your x variable is just your extension. So m is the letter we use as the general slope. But what is elastic force equal to? What's the formula for elastic force? Fe equals, sorry? That's not the formula for, that's a truth if the thing's not moving. Kx. So if Fe equals Kx and y equals mx, what should the slope of your line represent? Compare the equations. If y equals mx and Fe equals Kx, then m is going to be your K value. So the slope of your line of best fit should be the spring constant. And that's how you're going to find this thing. And then there may or may not be a y-intercept. We'll see how it goes when you draw your line of best fit. So everyone, every partnership, I want you to work in pairs because there's an even number of you here today. Grab a scale, grab a rubber band, and start hanging things. What the? It sounded really bad. What is going on?